and that is we're going to treat this as though it is a non-rigid body member. In other words, we already know that if this is a cable here, for example, then the force would be a single force along the direction of the cable. We've seen that. When it comes to springs, same thing. There's nothing different here. So if I want to show this force on a free body diagram, it is merely going to be a single force drawn like that. It honestly doesn't get much easier than that, folks, but I wanted you to have that. We're going to see how that's actually done, used in action. It is worth noting, too, that there are spring configurations out there. There are torsional spring configurations. We're really not going to do anything with those, so I'm not going to worry about that, other than I would simply tell you that a torsional spring does exactly what it sounds like it does. It creates torsion, or it creates moment on something, but we're just not going to do anything with that. So again, I just wanted you to have that background. If we see a spring, it's really easy to figure out how to represent springs. Again, just think of the line connecting the two ends of the springs, or the spring's axis, if you want to think of it that way, and it's a single force along that line. So now, having said all that, and I'm going to work from, again, this is the document that I put up and available for you on Blackboard here. I want to work from this document. Here's the game plan. I'm going to work through a number of these free body diagrams. There's a bunch of them that were given to us in that document that had some forces on them already, but the forces weren't complete. So the objective was to complete the free body diagram. And then there was a section of them that had either incomplete free body diagrams and or incorrect free body diagrams. And the objective in that case was to get the right free body diagrams. So what I want to do here, folks, to get everybody prepared to do this, is I'm going to put an object or a sketch up here on the board and point out what we want to do a free body diagram of, and then I'm going to shut up for about 3 or 4 minutes and I want everybody in the room to draw your version of the free body diagram of what you think the free body diagram should look like, and then we're going to look at that. We're going to compare and see, all right, this is what it should look like, how does it compare to what you did, and then you can, through that mechanism, of course, find areas that you may have some need to fill as far as understanding and such like that goes. So let me draw the first thing up here, and then we'll talk about what we want to do, and we'll go from there, but get ready to draw a free body diagram accordingly. So 2 seconds to knock this out. Now, folks, as you know, it is critically important, and this goes right to our free body diagramming, it is critically important to make sure you listen carefully to what the narrative says. Hear this. What we see here is a control lever applying torque to the shaft at point O. So control lever applying torque to a shaft here at point O. That. Folks, take a few minutes, draw the free body diagram of the control lever. We're going to isolate and draw a free body diagram of the control lever. If you're wondering, and I normally wouldn't do this, but this control lever continues on like that, so it's got a pin going through it like so. So take a few minutes, do that, and we'll come back and talk about it. take about maybe about 1 more minute, folks, if anybody is still working on it, to try to wrap this one up. Okay, so folks, to do the free body diagram of this, and again, in just a little while, we're going to be having an evaluation, right? Little mini quizzes, we all call them, or know them. And this is what I'm looking for, okay? This is what's going to lead to the 10 points on that thing. Number one, did you follow the 4 steps? Where the first step was doing nothing more than sketching an isolated version of the thing that we want to do a free body diagram of. And I've already done that wrong, but okay, easy to fix. So did you do this? Well, we need a pinhole there, don't we? If, as you did your free body diagram, if this is the first step that you did exactly what you're supposed to do. That's the right thing to do. Sketch the thing that we want to do the free body diagram of. Secondly then, now that we've got that sketched out, secondly, and by the way, it doesn't matter what order you put these things in here, folks, whether you call this step 2 or step 4, did everybody include a coordinate axis system when you did your free body diagram? If your answer is yes, I did, you did right. If your answer is no, I didn't, you do not get 10 points in a little while. You must include the coordinate axis system. There's no ifs, ands, or buts, and it's not like it's a hard thing to do, right? So you gotta do that. Okay, secondly, or I guess thirdly now. Now, we've got the sketch. It's isolated, there's no ghost lines, there's no dash lines, there's nothing like that. We got a coordinate axis system, fantastic. Now, we need to apply or show any forces that were applied to this thing. And going back to our original, we did have one applied force here, it was force P. So force P should be shown on your free body diagram, and it should be shown exactly the way that it is shown in the original, no problem. Now, you ask yourself, what did this thing weigh? Did we have any information about that? If you go back and look at the narrative said, control lever applying torque to shaft at O. It said nothing about weight. It said nothing about mass. So we're not going to make anything up. We don't guess or anything like that. So in this particular case, since there was no mention of mass or weight, we don't need to worry about that. Now, though, is where, and this is the critical part, now we got to go around and look at this and say, I need forces, whether it's linear forces or moments, I need those wherever this object used to be in contact with something. So if we look at this, nothing's going on here, but all of a sudden, right where I'm pointing here at point O, we used to be in contact with something at point O. Now the question becomes, well, what is that? Well, the easy way to see this is to recognize that that is in fact nothing more than a pin, right? So that is a pin. We should all already know that when it comes to pin forces, we automatically represent those with an arbitrary x direction force and an arbitrary y direction force. That's just always going to be the case with pin forces, always, right? So you would be absolutely correct if your free body diagram showed, let's say, an x direction force. Let's say we call it O sub x, and by the way, you call it whatever you want. An x direction force and a y direction force like that. Let's call that one O sub y maybe. Now, let's also remember that the directionality here was purely arbitrary. We have no idea if OX is really going that way or if it's really pointing back towards me. Just like we don't know if OY is really going up or if it's really going down. It makes no difference. So if on your sketch, if you chose to show OX this way, no problem. If you chose to show OY that way, no problem whatsoever. So a general representation though, that's all you're looking for. And let's remember too, we talked about this, if at any time you're not sure about that, if you are not certain whether or not there should have been an X direction force and a Y direction force, think back to what we talked about the other day. What is our way of knowing? The answer is we know by asking ourselves if this pin really was still in place here and I tried to cause translational motion. If I tried to take this thing here and tried to move it in the X direction with that pin in place, linear translational motion with the pin in place, would I face resistance to motion? Heck yeah. So if you face resistance to motion, force. Same thing, I grab this, I try to move it up and down in the Y direction, pins in place. Would I face resistance to motion? So therefore, you gotta have a force there. Of course, if the answer to either of those questions was no, I would face no resistance to motion, then there's no force there, just that simple. So now, I'm not looking for a show of hands or anything, but I want you to look at what you've got right here and ask yourself, did you get that far? Did you get these things here on your free body diagram? And again, if the answer is no, we've got to fix that. Folks, you got to hear me when I say this. You got to know. Doing free body diagrams right is everything. So if you didn't get this one, okay, no problem, because we're early on, but we got to get to the point where we know how to do this. Now let me ask you a question. And I'm welcome to see a show of hands in this case. How many of you would agree that that free body diagram is complete? Okay, see a few hands are popping up, not many, not many. For those of you that think it's incomplete, what did we forget?
I included a moment on mine.
Why'd you do that?
Well, because if it's on a pin and there's a force pushing it upwards, it's going to want to kind of rotate counterclockwise possibly.
Exactly. But I want to take it a little bit further than that. You are right. You're right. But remember, if this pin, if we had anything in our narrative that led us to believe that that was a smooth connection, then if that's a smooth pin I should have said, if that's a smooth pin, then there would be no resistance to rotation at all, right? None. If there's no resistance to rotation, no moment. However, one last time, read the narrative. The narrative said, hear this, control lever, quote, applying torque to the shaft at O. If the control lever is applying torque, then it's putting a moment on that. In other words, there is resistance to motion there because it's applying torque. What they're really saying here, without saying it, is this is not a smooth pin. This is actually a pin that is effectively connected to the shaft right here. Therefore, there's got to be some sort of a moment associated with this. So the complete free body diagram would show a moment. And you call this, again, whatever you want to. Call it M sub O, whatever. It doesn't make a bit of difference. But there would be a moment there. Now, as is always going to be the case, we can assign directionality in an arbitrary way. If you notice the moment that I drew right here, about point O, you'll notice I drew this as a clockwise moment, right? Now, I drew it as a clockwise moment because in this particular instance, I know that force P is going to cause a counterclockwise moment about point O, and I know that this moment's got to counteract that. That's why I drew it clockwise. Had I not done that, no big deal. The math, if I'd drawn the moment in that case in a counterclockwise fashion, then the math would have simply said, yeah, your moment is negative, and the negative in this case means you went the wrong way. That's all. Nothing to it. Now that right there, folks, is the complete free body diagram of this. And let's do the checklist here. Did we have an isolated sketch? Yes. Did we show any applied forces? Any applied forces that were on that particular object? Yes. Did we show forces and moments when they're there? Did we show forces and moments at all places where we used to be in contact with something, and the only place we ever were in contact with anything was on that pin? So yes, we've done that. Did we include a coordinate axis system? Yes. It's all there, folks. Were there any relevant dimensions or anything like that that should have been included on this free body diagram? The answer is no. First of all, we weren't given any. But even if there was, do remember that free body diagrams don't need to include dimensions or angles, although sometimes it's pretty smart to do so. And there you have it, folks. So again, take one last look at this one here. Again, if your paper didn't go this far, you just gotta, and again, nothing's wrong, but you gotta look at it and say, okay, I missed that because I didn't understand, and then fill in the blank. And then you need to understand that. These are the kinds of mistakes that we just can't make. Okay, let's do another one. Okay, folks, so what we've got here is boom. A boom here, we're defining the boom by these two labels here. So let's call this boom OA. Let's hear the narrative on this one. Boom OA of, hear this, boom OA of negligible mass compared with the mass M. So what we're saying is, whatever the mass of this boom is, it's nothing compared to the mass of this. Now that is indirectly saying to you, we don't care what the mass of the boom is. All right? In other words, you don't have to worry about its weight. Boom is hinged at point O and supported by a hoisting cable at point B. Folks, let's do a free body diagram of just boom OA. Seconds to make sure everybody's had enough time to sketch this one out. All right, so let's do the same old here, folks. And by the way, as we do this, we're going to go quicker and quicker. All right, there's no need to go through in so much detail with every one. So we want to do a boom OA. Starts with a sketch of said boom OA. That's literally it. So right off the bat, we've got that sketch of the boom itself. Here's the place where the cable is connected in. Here's the place where the mass is hanging there. So now, If your free body diagram included a picture of just boom OA, as you see right there, you've got the right sketch. And remember, this is one that, you know, you could arguably say, but shouldn't I include the mass on that? Well, you are actually, but not in the sketch of the free body diagram itself. If all we're looking to do is boom OA, then all you draw is boom OA. So that's what your sketch should look like. And of course now, this next step, the coordinate axis system, nothing new there. But now let's start thinking about this. First up, we got the sketch. We have to ask ourselves, was there any applied forces here? The answer is yes, there was. All right, the applied force was the force due to this mass right here. So mass, of course, we got to convert that over to weight, right? Is a mass, by the units of mass, is that a force? Is that a weight? Of course not. What do we need to do? Somebody tell me, what do we need to do to convert a mass into a weight? We need to multiply by G. Gravity, exactly. Multiply by gravity, G. So in this case here, we're going to show the weight of this, and you call it, again, whatever you want to, but since it's a weight force, how about we use, in this case, the mass m that we were given, multiplied by just the gravitational constant G. If you did that, 2 seconds, if you did that, there's nothing wrong with that. If, on the other hand, you simply just put this down as W, fine, but that W will have to be converted into the right, you know, weight when you do the work on it. Yeah, far away.
Since it's connected to the boom via like a rope or a cable,
Yep.
tension there because there's a force of tension.
Yeah, we're going to get to that in 2 seconds, but yeah, 100% right, absolutely right. But I want to, before I go there, I want to make sure everybody's seeing this. So, a couple things about this. If you're given a mass, mass must be multiplied by the gravitational constant to convert it to a weight, always. On the other hand, if you're given a weight, if you're told this thing weighs, I don't know, 100 newtons for 100 pounds, both of those are already in weight units. Never do anything more to that. A mistake that gets unfortunately made somewhat often is, hey, here's something that's 100 newtons, and somebody will write down then, oh, then the weight must be 100 times 9.81, so 981 newtons. No, it's already 100 newtons. You didn't multiply that one by 9.81. On the other hand, if you're told it's 100 kilograms, well, yeah, then that one you multiply by 9.81 and turn it into a weight. So you got to make sure you know that. The second thing and the most important thing, folks, and I alluded to this the other day, whenever we draw a weight on any free body diagram, the direction of the weight must always point right down, straight down towards the center of the earth. Always. Okay? There is no scenario where the weight is going off in any direction other than straight down. Okay? Very important piece. So now, there's our applied force. What about the weight of the boom itself? Well, remember the narrative told us that the weight of the boom, or the mass of the boom is what the narrative said, the mass of the boom is negligible. Right? Negligible. So therefore, we don't need to worry about a weight on the mass of the boom. Nothing, Burger. Okay, fine. Now to the very good point about the cable. Now what we're going to do is we're going to work our way, and I was kind of, personally, I always like to just kind of do this in my head, like just kind of work my way around. So, all right, where did I used to be in contact with something? I used to be in contact with this right here, but I've already taken care of that. I've showed that as the weight force, so done there. I used to be in contact with a cable right here at point B. Now, correctly pointed out, the cable must be in tension. So that free body diagram aside, if I did a free body diagram of the cable, then I already know that the only force that can exist on the cable has to be drawn as a tension force. My arrows have to be pulling away from that. That means that this force here, which maybe we'll call it, let's just simply call it T for tension, that this force here has to be represented right here, but equal and opposite, right? Equal and opposite. So it's got to be going back the other way. And this reminds us that whenever we're drawing a force associated with a tension member, cable, belt, rope, whatever, then that is simply always just going to be an arrow along the line of action of that cable pointing away from the object. Did you have another question?
I was talking about it, A, since the weight or the mass is connected to the boom via a cable, would it be a force of tension? Or is that
Same idea. Okay, so think about this. It's a good question, and I misunderstood. I thought you were talking about the other cable, so I'm glad you clarified. If we break this down, all right, if I just really free body diagram with a cable here coming off of that, then this force here must go that way, this force must go that way. If this one points up, this one's got to go equal and opposite, and it's going to be the same as the weight of the object that's hanging from it. Exactly, exactly right. So we've got that one taken care of. Lastly, and again, here now is where in these last forces, this just needs to become set in nature. I don't even think about it. I got a pin down here at point O. If I have a pin, then I've got an OX and I've got an OY. Again, do I know their direction? No. Do I care? No. Because my math will straighten me out on that. Now, that right there, folks, I want you all to know, that is the complete free body diagram for this one. Now we are seeing the exact opposite of what we saw in the previous problem, where in the previous problem we did include a moment down here, but there was something in the language that told us we had to do that. Here, we're not doing it. We didn't include a moment. Why? What do you think?
It doesn't say torque.
Exactly. Nothing was said about it. In other words, there was nothing in the narrative that said that this was a rough surface, that there was a torque applied or anything like that. The narrative, quite frankly, was silent on this. Didn't say a thing. So when the narrative is silent about whether a connection is smooth or not smooth, if the narrative is silent on it, we assume it's smooth. We assume there's no friction there. So in this case here, we would not have included a moment here because we got no reason to think there's a moment there. And with that, think about what we did. Sketch, apply forces, forces where we used to be in contact with something, coordinate axis system. Boom, 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 done. Questions on this one? Anybody? Yes? For A itself? Okay, so I'm gonna make sure I heard your question, okay? And if I'm answering it wrong, stop me, okay? I think what you were saying is, would there be more up here? Would there be like a X force here? Yeah? So if you think about what's connected here though, never mind this, it's just a cable, right? So any time we have just a cable, it's always just one single line drawn in the direction of the cable. So in this case, since the cable is up and down, it's just a single arrow up and down. There actually wouldn't be any kind of an X force here for that one. It's a good question. Any other questions, anybody? Yeah?
If we were to draw tension with a dual arrow, like an arrow pointing that way and that way, would that knock us points?
Yes.
Yeah?
Yeah, absolutely. So I want to make sure I understand, and again, if I'm saying this wrong, stop me, okay? So what I think I heard you say was if I had a tension member like this cable right here, if I showed directionality like this and like this, is that what you were asking?
No, just like if since tension pulls both directions, if I have an arrow pointing this way and an arrow pointing that way, would that knock us points? Not anything in the y direction.
So are you saying here?
Yeah.
Yeah, it would. Because if you think about what I'm hearing you say is, you're saying, could I show an arrow this way and then another one over this way? Is that right? Yeah, so if you think about it, well, first of all, just simply put, we don't do it that way. So that's just the standard way of how we show a force in a tension member, like this cable here. The standard way is simply one arrow, okay? If you think about what the net effect would be, if you put, as you suggested, this arrow this way and then another one over going the other way, remember that forces on the same line mathematically add. So what you basically did was said, I got nothing here now, because this one here subtracted from that one means I got nothing. So yeah, it's a good question. It's a good question. And folks, y'all need to hear, answering these questions like, hey, I don't get this, I'm not sure about this, this is precisely what you want to do. If you've got any uncertainties, ask the questions, because that's how we figure out how to do this. So don't be bashful. That's a great question you ask. Any other questions, anybody, feel free. And you got a good question too. This is how we understand these things. Sweet, all right. Let's do another one. But by the way, in doing these first two, do you guys get the sense that the first two things we looked at were actually pretty easy little mechanical systems? There wasn't a whole lot going on. And yet, in doing the free body diagrams of just these easy little systems, are we not all seeing how it'd be easy to like get a little confused or make a mistake, right? So think about how it's going to be when the systems get a lot messier, when we get away from the easy stuff. This is why we got to do this right now and really understand it. It goes so perfectly to that thing with, that I know we all hear about, we all know about, and that's the idea of, I saw you do it on the board, it looks so easy, but then all of a sudden when you got to do it, it's not quite that easy. So that's why we're doing these things, folks. So let's take a look. Next one here, this one is a pretty straightforward one. Now, folks, the drawing on this one is super simple. The artwork on the original here is a little bit busier, but just so we all know, what's leaning up against the wall on the floor here is a crate. So think of it as like a big wooden crate, all right? Let's read the narrative here. And again, the narrative here is extremely important to understanding this one. Hear this, the very first word in the narrative is uniform. Uniform is an absolute must-understand buzzword. Whenever we say that something is uniform, what we're saying is it is spatially symmetric, all right? It's symmetric. If you drew a line through it this way, it's symmetric. If you draw a line through it this way, it's symmetric, all right? And that all of any mass that's got, it's uniformly distributed throughout. So in other words, it's not like this thing weighs 500 pounds over here and 2 pounds over here. It's all uniform, and that's a very important concept for us. When we see the word uniform, what that means is that means where you show the weight is going to be in the geometric, or I should say, passing through the geometric center of whatever that thing is. If something is uniform, the weight goes through its geometric center. Now, having said that, uniform crate of mass M, so we know the crate weighs something. The uniform crate of mass M leaning against smooth, there's the buzzword, smooth vertical wall and supported on a rough horizontal surface. So folks, rough surface down here, smooth surface here, uniform of mass M. Let's do a free body diagram with just that thing right there. seconds, folks. Let anybody still working on it finish up. All right. So the free body diagram of the crate. Here again, if you just follow the steps, you got this one. So in this case, we know what we want to isolate. It's the crate. So let's draw a sketch of the thing that we want to isolate, i.e. the crate. So there's our crate, there's our sketch. That part's done. Next up, axis system. Now in this case, folks, again, all you have to do, all you ever have to do is just that. Just that. A day is going to come when we're going to look at certain free body diagrams and realize that if we rotate that axis system, we make our math easier. But even if you don't rotate it, it's not wrong. There's nothing wrong. So sketch, axis, good. Now, if we go back, we were told that this was a uniform crate of mass M. So we know the crate weighs something, right? By the mere fact that it's uniform, that means that the weight must be passing through the geometric center. Now, I'm just going to try to lightly, and I'm going to erase this. That was a bad move anyway. If I drew a light line from here to here and a light line from here to here, that was my geometric center right about there, right? So, let me get rid of this. I'm not supposed to add lines. I don't need my free body diagram, but I want to kind of illustrate what I mean by the geometric center of this thing. Right there in the center of this crate, I've got to show the weight before I do anything else. Folks, what is the magnitude? We were told that the mass here was merely M. So before I even draw my arrow up there, what magnitude should I show on that arrow? What's the right thing to show on that arrow? Anybody? mg. When we only know mass, we're just going to write down mg every time. Now, anybody or everybody, blurt out, what direction is that arrow pointing in the crate? Straight down towards the center of the earth. So I can anchor it right there. I can pass it anywhere I want on its line of action. It doesn't make a bit of difference. But I need to have a weight going straight down. And as we said just a moment ago, the magnitude of that force is simply the mass times the gravitational constant g. Now we were told that we had a smooth vertical wall. Now we're at the point where we're going around this thing. You're literally going around the horn and saying, okay, where did I used to be in contact with something? I used to be in contact with the wall, the vertical wall, right there. So folks, since that is a smooth wall, that means that the force here has got to be, and remember, we talked about this the other day. If you think about the point of contact here and the surface upon which it's contacting, think about a tangent line, but the tangent line in this case is, in fact, as we said, if you got a flat surface, that is the tangent line. So the single force here has got to be drawn normal to the tangent line, or normal to this line here, which means over here, I'm going to show a single force, like so, and call it whatever you want. Let's call this force A, for example. Just like that. Now, do I know that that's the directionality of that force? I do actually, but I don't need to. The reason I say I do is this. I know it's the directionality because the weight of this is going to cause the box to lean against the wall, and the force I'm showing here is the reaction. So if the box is pushing a force this way against the wall, this is the force pushing against the box. I'll come to you in 2 seconds. Had you drawn your arrow this way, great. If you drew your arrow the other way, fine, no problem. Because remember, the math will show you the right direction. Yeah, go right ahead.
So would it also be okay if you put the table on the inside of A and the end of just on the inside of M?
It's a fantastic question, and the answer is absolutely okay. Your question, I want to make sure everybody hears it because it's a great one. Your question is, what if I drew my arrow instead of the way I drew it here? What if I drew it so I anchored it right here and had the arrowhead over here? Did I get that right? Remember, folks, and this is important for all of us, we have a line of action of this force that goes forever, right? The line of action here goes forever that way, and it goes forever that way, which means I can slide this force anywhere I want to on its line of action, and I'm perfectly fine. To your question, if I had shown this force as anchored right here and an arrowhead over where my pen's at right now, great. What's interesting is if I showed this force like over here, right? I still solve the problem. The math gets a lot, well, the math starts becoming absolutely shitty, but you know, you wouldn't do that, but it would still be right. It's a great question. Now, since this was a smooth surface, there is no other force here. And again, when you're not certain about that, remember, if this surface is smooth, if this surface here is smooth, and you took the crate and tried to move it up and down that surface, which has no friction, would it face any resistance to motion? No. If there's no resistance to motion, you can't have a force in that direction. However, down here at B, the only other place that we were in contact with something, we were told that this surface here is a rough surface. So in this case, two things. Number one, we know we're going to have a normal force. That's, again, a force that's going to be normal to the tangent line, which is going to go, in this case, straight up and down. And if you're not certain about that, again, take the box. If you try to shove the box through the floor here, is it going to face resistance to motion? Yup. So therefore, there's got to be a force there. So I would show a force like this. Maybe I call the force By, maybe call it N. It doesn't matter, right? Call it whatever you want. As long as you don't call it A, you already used up A. But now we were told that this was a rough surface, meaning that if I take this box now and try to move it across the rough surface in the x direction, would I face resistance to motion then? Yes, because of friction. So therefore, I gotta have a force, right? Now, I'm gonna draw my force in here. The next question becomes, does it matter which way I draw the arrowhead? The answer is no for now, but yes for later. All right? When we start studying friction, it's going to matter. But for right now, if on your free body diagram, if you drew your arrowhead pointing that way, no problem. If you drew your arrowhead pointing this way, no problem. But let me tell you how we're supposed to do it. Ask yourself this question, folks. If this crate here actually did start moving on its own, now first of all, why would it move on its own? The answer is its weight might cause it to slide down the wall and slide along the floor here, right? If this thing started moving on its own, just think about the corner of the crate right here. What way is the corner of the crate going to go? Is it going to go to the left or to the right? And I'm seeing a lot of fingers pointing to the right. That means that the direction of impending motion, in other words, the motion that would take place, the direction of impending motion is that way. Friction must always oppose impending motion. So if the motion's that way, then the friction's got to be going the other way. So the correct way to show this would have had the arrowhead going like that. But again, we're not worried about that for right now. That's going to come into play in chapter 6, but I'm kind of giving you a preview of what's, things yet to come. But these kinds of mental things too are also, hugely valuable for us to understand, the right way to do free body diagrams. Folks, if that's what your free body diagram looked like on your paper or electronic device, whatever you're using for this, that's exactly the way it should look. That's exactly what it should look like. If again, you missed something, and again, nothing's wrong with missing something at this stage, we're learning, right? But again, you want to make sure you don't just shrug it off. Ask yourself, why did I miss that? Why did I not understand that? And fill in that blank. You got to fill in the blanks, everybody. Does anybody have any questions further on that one right there? Yes, fire away.
Is there any moment created around the center?
Good question. Oh man, that's a great question. Now, I want to make sure I heard you though. I think you said, is there any moment created around the center? Did I hear that?
Yeah, that's how I at least envision it, but I guess it would be around the entire crate.
Yeah, and actually the answer is no in all cases, all right? So we don't have any impending rotation here, all right, around the center, because we're not contemplating that. And I know that's a really vague answer, I get that. But in this case here, we're only looking for reaction forces. So if you put a moment in the center, that's a reaction force. It would be a reaction to something taking place, and we don't have them here. We only have reactions where we used to be in contact with something. Okay, that's the importance of that used to be in contact thing. Now, it does though, your question gives rise to the idea, should I have a moment right here? if this thing were to rotate, would I expect there to be any kind of resistance to rotation on that point? That is arguable. If there was a pin there, absolutely. All right, if there was a rough pin there, absolutely. But on the rough surface, the question becomes, is there anything, like if I've got a, well, use my pen right here. If I dropped my pen right now, did it look like it rotated about that point? Yes. But was there any resistance to that rotation? I don't think there is, so therefore we wouldn't show that. Great question, fantastic one. What other questions? Any others? Again, folks, I want to be clear. I appreciate all these questions. Lay it on me. What you got?
So, saying that on the first free body diagram, you had the circle around the pin, but wasn't it a smooth pin? So would you not have one around a smooth pin?
So you referenced the first one we did, right? And that was the one that had the lever that came down. There was a crank out here and we pulled up the P. The only reason, good question, but the only reason that we showed that moment in that case was because the narrative told us that it was actually applying a torque, which means it's putting a torque on that. Yeah. That's why. And that's why, again, and why your question's so good. Again, folks, you got to realize drawing free body diagrams is always more than just the sketch and following the rules on forces. It's doing that in the context of what did the narrative tell me. And these narratives, as we've already seen, you got to kind of sometimes really read the words and understand the buzzwords in there, right? You might not notice that the word uniform means something, right? Or applying torque means something. So yeah, it's a great question. Anything else on this one? Yeah, fire away.
So can we use moments when there would be a resistance to rotation, not just a rotation in the system?
Both.
Okay.
Both. That's a great question. If I had, for example, if my pen was in some sort of a bearing surface and there's friction on that and I'm trying to rotate that, if there's resistance to that rotation, then yes, there's a moment drawn there because of the resistance to rotation. Same thing. If I clamp down on this and now when I rotate the pen, it's trying to rotate me with it, it's also resisting motion, so there would be a moment on that too. Great question. Anything else, anybody? Cool, love these questions. Let's see where we're going from here. We're going to do just a couple more and then we'll move on to the evaluation. Just to give you guys kind of a sense of where we're at with all of this. All right, folks, just like the other ones we've done so far, the narrative on this one's going to matter a lot. So, okay, it goes like this. Loaded bracket, supported by pin connection at A and fixed pin in smooth slot B. Now, I want to preface this. Even the narrative on this one's a little ambiguous, all right? It went so far as to tell us that this slot here at B was smooth, and it mentioned pin A. But it didn't say whether A was smooth or not, right? Told us this was, didn't tell us anything about A. But remember the rule, if the narrative is silent on that, if it doesn't tell us one way or the other, we assume it's smooth. So since the narrative didn't say rough pin A or friction pin A, it's a smooth pin. So that's smooth as well. Loaded bracket means there's just a load force that's already on this bracket right here. So we got this bracket, as you can see, it's meant to be illustrating this like pinned to a, like a wall or some sort of a member like that right there. So in this case here, folks, we want to draw a free body diagram of the bracket itself. Just the bracket as you see right here. Let's do that free body diagram. Yeah?
What do you say in regards to the pin and B? Yeah, what do you say in regards to that?
Just that this slot right here is smooth.
Okay.
What was L again? What did you say L was?
L is just a force. It's just an applied force.
Oh,
It's
okay.
a load.
A load.
Yep. Just another few seconds, make sure everybody has a chance to finish it. Okay, so folks, success on this one here is driven entirely by just following again the little recipe, the 4 steps, okay? It starts with sketch the object, isolate it. So this was the thing we wanted to sketch. So a quick, doesn't have to be really beautiful or anything, just a quick little sketch of this. We'll have the slot in here, we'll have the pinhole down here, and that's it. If you think about this, this sketch here represents this thing here, isolated, it's not touching anything. Now, I'm gonna guess that some of you included the pin inside of here in your diagram. Unfortunately, that would be a mistake because it would be showing it not completely isolated. It's still touching something, all right? So you wouldn't do that. So now, with that, and I'm going to skip the coordinate axis system for just a moment. I'll come back and get the coordinate axis system in just a moment. So we've got our object. We were told absolutely nothing about the weight of this thing here, so we don't have to worry about weight. That's good news. We do have an applied force here, and this is arbitrarily assigned force here, going off apparently like that, and it's called L. So as it stands right now, I've got my object drawn. I took care of the weight, which in this case did nothing. I've got my applied force L, and now I'm down to, I just need to put forces in where I used to be in contact with something, all right? Now, in this case here, let's just talk about this before we actually put the forces in. Let's talk about this. I have a pin right here, which means I'm going to have an X force and a Y force. Pins, X force and Y force every time, right? We were told that, well, we talked about this before we did this. This is smooth, so therefore there's no moment here, just X and Y force. We also had a smooth surface up here. Because this is a smooth surface, if you think about the pin that's right here, if I try to move this thing in this direction here, the smooth surface means there's no resistance to motion. On the other hand, if I try to take my bracket and shove it against the pin like this, I would have resistance to motion, all right? Now, because of that, this is a great example of when you assign your coordinate axis system, it probably makes great sense to assign it so that your X and Y axis gives you one axis that's in line with this sliding plane. You don't have to. There's nothing wrong if you didn't, but I'll show you in a second why it makes the math easier. So now, if I do that, then that means down here on my free body diagram, my pins have an X direction force, and pins have a Y direction force. So I could have a, let's call this one AX. I could have an AY force. Do I know that directionality? Nope, no clue, no idea whatsoever. So I just take a wild stab, right? Perfectly good. Now here at B, we've already asserted that we would have no resistance to sliding this way, but we would have resistance to sliding this way. That means I'm going to have a single force here, normal to the plane of contact. There's our plane of contact, and call this one whatever you want to call it. I'll call this N for normal, right? And there's your free body diagram. Even though my arrowhead here is kind of crappy, let's make sure we see it just. And again, do I know that that's the direction of the arrowhead? Nope, no clue, right? But I'll let my math worry about that. And that right there is the entirety of the free body diagram. Now, again, if I chose to do my X and Y axis system the normal way, no problem whatsoever, but just realize that you would have to convert this into its X and Y coordinates, resolve it into its X and Y components in order to be able to solve that force. You gotta do the same thing here, and this is probably still okay. By rotating the axis here, I made this a purely Y directional force. I made this purely X, and that's purely Y. The only thing I'd have to resolve would be this force right here into its X and Y components in order to solve this. It makes the math a little bit easier by recognizing that opportunity and rotating your axis system. But again, if you don't, it doesn't really change anything. It just makes the math, in some cases, a touch harder. Yeah, far away.
If we took the coordinate axis system kind of like standard, would we be wrong in putting like a straight side to side force where the pin comes to be in contact with the slot?
With the slot, right? Boy. The technical answer to your question is you would not be wrong. And I'm going to show you why. This is a great question. But the strong caution I would have is that you want to get used to, though, just drawing a single normal force. But to your point, had you used an X and Y coordinate axis system, then like I said, this normal force here would have to be eventually resolved into its components, which means that it would be correct to have the components shown too. I don't encourage that, but to your question, it would be okay. Yeah, good question. Yeah.
Isn't there like normal force opposing gravity, so wouldn't it be like a vertical?
No, no. You're talking about this one right here? Yeah. So the answer again is no, because it's not just opposing gravity. All right. It's opposing the gravity of this if it had a weight, but it's also opposing this, and it's also opposing the reaction here as well. So since we don't know that, we just stick with the convention. The convention is plane of contact and normal to the plane of contact. Yes?
Wouldn't there also be another normal force to the other plane of contact?
You talking about up here?
Yeah.
Yeah, great question. I was hoping somebody asked that question. So I want to make sure everybody heard it because it's really a salient question. Your question was, well, what about, would there be, since we may have had some contact up here, would there also be another force here? The answer is not really, but yes. Yes, meaning that if there is contact up here, then there is a force there too. If there is contact down here, there's a force here too. The reality is we don't know. So what we do is we show it as one single force, and we figure out what the total reaction is on that, and then that's going to be distributed depending upon how the contact goes. That's getting way out ahead of our skis, but it's a great question. It's a very good question. I think a better way to say that is, it's true that there could be a second force there, but we simplify it by just showing one. Good question. What else, folks? Love these questions. Okay, let's, again, I want to do just a couple more, and then we'll move on. We'll be done with this. There's sure not a lot to the diagram on this one here, folks, and there's not much in the narrative, but the narrative tells us everything we need to know here. Here's the narrative. Wheel of mass M. So we know that this wheel has a mass M. Wheel of mass M, here are these words, on the verge of being rolled over the curb by pull B. So this force here is pulling the wheel this way. The language is on the verge of being pulled over the curb right here. Let's do a free body diagram of just the wheel. Okay, folks, so the free body diagram on this one, we're showing the wheel. We're showing the force P pulling on it. Let's give ourselves an X, Y axis system. And then go from there. The narrative told us that the wheel has a mass, so we know there's going to be a weight. It didn't say the wheel was uniform, but circles are uniform. So therefore, the geometric center of the wheel is where we should show the weight. So straight down towards the center of the earth, mg, like so. And then we do the same old, same old. We ask ourselves, where was there points of contact and what do those forces look like? In this case here, we certainly, as this is being pulled up over the curb, we have contact right here, right? We have contact right there. And if you look at this, folks, I'm gonna try to draw this somewhat carefully here. There's a tangent line that goes kind of like the way my red line goes right there. Therefore, I would have a force that's normal to the tangent line. And by the way, normal to the tangent line and pointing right towards the center of the wheel. So it would go kind of like what I'm showing you right here. Now, were we told anything at all about whether the point of contact there was smooth or rough? The answer is we weren't told anything. So we, again, if the author or if the problem is silent on that, we assume it's smooth, even though I think everything in our being is telling us there should be a force going this way as well. But in the absence of that, just a normal force, yes?
If it's being rolled, doesn't there have to be friction?
Well, that's the question, right? It's a great question. That's why I said every bone in our body is saying there's got to be something there, right? But since the rule that I'm trying to impress upon everybody is if the authors are silent on it, we can't assume it's there, okay? So the author said nothing about whether this was a rough or a smooth surface. So go back to again, if you imagine that we set up a axis system that looked like this right here, X, Y. Geez, suddenly I can't draw a Y. So if I tried to move this, if we assume that surface there is smooth, and I try to move it this way on the smooth surface, would it face resistance to motion? No. If I try to push it into this corner here, would it face resistance to motion? Yes. So the answer is no, it would just be this. Now, on the other hand, if we were told this is a rough surface, absolutely, there would have to be something there. It's a good question. Clear?
I was just focusing on the word roll. Because if there was no friction, you could have it just go like this instead of like this.
But, yeah, what you're saying is since it's rolled, do we treat that differently than translational motion?
Or as if there's friction.
I think that's what you're getting at.
Yeah.
Again, though, we're not told there's friction there. So in the absence of that, I still would say no, all right? But I definitely see your point. Definitely see it.
If you keep the coordinate axis system, just straight up into the side, with that normal force, there's an X, Y component anyway, so even if it was deep rough, you
Yeah.
still draw the same.
Yeah, but that's a mathematical construct, right? So you're 100% right. The mere fact that we initially drew it like this means that that's going to be resolvable in X and Y components, but we're doing that for analytical purposes. We're not saying that there's necessarily a value there, okay? We don't know there's a value there, so it boils down to. But also a good point. Yeah, this one's a little bit weirder, isn't it, folks? But we're not quite done with it yet, are we? Or are we? So right now, folks, and I want to clean this little piece up here. Right now, how many of you would agree with me that the free body diagram is done? How many of you would agree with that? Why not? Anybody? Yeah, that's the question, right? I think most everybody's looking at that saying, wait a minute, man, there's a contact right there. But is there? Remember the narrative. The narrative said very specifically, on the verge of being rolled over the curb, right? If it's actually on the verge of being rolled over the curb, then that means this will actually elevate and we will lose contact right there. Now, we all could argue all day long that it didn't say that the contact has already been lost. It said that it was on the verge, right? But it said it was on the verge of being rolled over the curb. So, right or wrong, what this particular problem is trying to teach us is that whenever we see a problem like this and we're told that something is on the verge of or is, I don't know, I'm trying to think of a way to synonymously say that, impending, like motion like that, what the author is trying to get you to do is to realize there is no contact there, and therefore you don't have to model it, and therefore you don't have to solve for it. So it turns out because of that phrase, that 3-by diagram there is correct and it's complete. Questions on that, anybody? Yeah, so again, I'm going to come to you and I'll come to you too in just a second. Again, we could argue about that, but the takeaway here is you're trying to be shown that whenever you get this language, we're giving you a free pass. You don't have to worry about that.
Yeah.
Fire away.
Wouldn't it still be, so if we're assuming no contact on, the ground there, wouldn't it still be rotating around where the normal force is coming from?
We still don't know if it's rotating or not. I know it says roll, right? But again, we don't know that. You can't read into it, I guess what I'm trying to say. Yes.
For the normal force, if we mark it as X and Y forces, should that be marked on?
Yeah, it's a good question. It's actually very similar to, I think, a question that came from over this direction a few moments ago, and I can't remember exactly who asked it, but it was a great question. So the question becomes, if you already know that this is going to be resolvable into an X and a Y force, could you do that? The answer is technically yes. And that was your question, I think, if I remember right. It's technically yes, but the danger, what you're literally doing is you're saying, okay, I'm going to blow off convention because that's not going to help me in my future, and I'm just going to do it my way. It's screwing yourself. That's what it boils down to, all right? Follow convention. Follow convention. Convention says, consider the plane, consider the tangent line, which we did right here, and know that you've got a normal force there. And I think this is important, the distinction. Convention lets us know we're okay and we don't have to make a mistake, okay? So if we always realize there's got to be a tangent line, we know there's got to be a force normal to the tangent line. In the absence of friction or known friction, we know there can't be a force this way because there's nothing resisting motion. So this is the safe bet. Mathematically speaking, does yours get us to the same place? Yeah, but it's dangerous. It's a great question, though. What other questions have you guys got? Oh, sorry. Thanks, I didn't see it.
The normal force on this one's pointing into the object. Why was it pointing out the object in the previous example?
I don't remember the previous example now.
It
Was that the bracket here? Yeah, remember, they're arbitrary. Draw in whatever direction you want. In this case here, I would argue, though, that if I'm pulling this way, this force has to resist that, so it's got to go that way. Okay?
So
But
like pointing it like coming like the opposite direction.
yeah, if I drew it like this,
Yeah.
you'll still get you're going to get the same result, but your math will tell you that this is whatever this number turns out to be, the math's going to say it's negative, which is going to tell you that if you chose to draw it this way and you came out with a negative, it's telling you that it's actually going that way. Yeah. That's the arbitrary nature of it. Other questions, anybody? Okay, cool. Last one, and then we'll move on to the eval. Folks, maybe do 2 free body diagrams for this one. in this case here, folks, I want you to do a free body diagram of that bar, and then a second free body diagram of that bar. Or bracket, I should say. Now, I want to make sure everybody's clear. This is a continuous bar here. That's just a pinhole in the bar. Just another minute or so, then we'll finish this one up. folks. So if you're still working on it, it's fine, but like I gotta start off here with just sketching the two different objects. So we got our isolated sketches, they're not touching anything. We've got the coordinate axis system in there. I believe, I'm gonna double check this here folks, but I believe the problem told us nothing about these things weighing anything. I'm gonna double check that. So yeah, it is nothing more than it says the supporting angle bracket for the frame pin joint. So nothing on the weight on this one here. So we've got the applied force F here for that one. Folks, let's make sure the applied force F was shown on this piece here. If you chose to show F anywhere on this thing right here, it's not on this thing right here, so that would not be correct, okay? F is up here, and easy enough to do that. Now, as we look at this, let's look at pin C. So, simple pin connection down here. Pins are pins, right? Pins are pins. Nothing said here about anything being rough or anything like that. So, simple pin connection would give us an X direction force. Let's call that CX. Let's have a Y direction force here. Let's call that CY. Then we look at pin B. Now, I'm going to show you two right answers for this one. All right, the first one here goes like this. You see that pin B is, again, nothing more than a pin. So since it's nothing more than a pin, it's perfectly fine to say, okay, then I got a BX and I got a BY. Do I know that that's the direction of those things? Nope, no clue. Do I care? Nope. Math will straighten that out. But now, that free body diagram for this piece here, correct, done. Worth noting though, if you were to try to solve this free body diagram, remember what's our budget for number of equations for each free body diagram in 2D world? It's 3 equations of equilibrium, right? I get some forces in X, I get some forces in Y, and I can take a moment about some point, 1 moment equation, right? In that case, I could solve the 3 unknowns. If I knew, for example, if I was told that the applied force F was whatever, let's say 200 pounds, then I would have a known here, but I have 1, 2, 3, 4 unknowns. I cannot solve that problem, all right? Or I can't solve that free body diagram. But if I go back over here to this free body diagram, then I got a pinhole here, which is pin B, and I've got to assign forces to that. What you must absolutely do is if you assign BX and BY on the pin here, you absolutely must assign BX and BY over here. But what's different, folks? Anybody? Opposite direction, right? So if you showed BX going to the right over here, then BX is going to be going to the left over here. BY was drawn upwards here, which means that BY has got to be drawn downward here. This right here, folks, that I just showed you is the #1 mistake that will cause you to have problems as we get deeper into the course trying to solve for machine problems and stuff like that. It's forgetting that you got to show the same forces equal and opposite. So if you did that on your free body diagram, if you've done this right here, you've done exactly right. Now we're not quite done because we got another pin down here at A. So why don't we show that pin here at A? Let's consider that we might have an AX, and let's consider that we might have some AY like that. Now, those two free body diagrams, and you remember I said at the beginning of this, I was going to show you 2 ways to do it right. That combination you see right there is one way to do it right. And if you think about this, now if you count up your grand total of your unknowns, I got 1, 2 plus the 4 that I already had. I got 6 total unknowns, 2 free body diagrams, therefore I got a budget of 6 equations. I can solve that, right? I gotta do a lot of math, but I can solve that. But I'm just curious, and I don't need to see a hand, but a nod of the head's great. How many of you recognized that that right there is a 2-force member? 2-force member. Why is it a 2-force member? Because it has a grand total of 2 pin connections, it has no weight, and it's got no applied forces on it, which makes that a 2-force member. So the other correct way to do the free body diagram for this piece right here would have been to make it look something like what I'm about to show you here. So there's our original bracket. And remember, for a 2-force member, the 2 forces existing on that have to go on a line that passes through the center of the holes, like that. So in this case here, it would be correct to show two forces, one here, get rid of this thing in between. Do we know the directionality of these forces? Believe it or not, we actually do. Because this force here, because it's pulling this way, it's going to try to cause tension in this. It's going to try to make it go this way. So that means the reaction forces on this would be going the opposite way. But again, if you didn't catch that, who cares? But this force and this force here are the same. So we could, for example, we could just call that force AB. We could call this force AB. But why is that valuable? Because now, when we come back over to this object and its free body diagram, so here's that object, pin, we got force F here. I'm going to just use the black pen for this. We got our CY and CX down here. So here's CY, here's CX. But folks, for right here, since we've already defined AB here going that way, then I could have AB over here going the opposite way. And that's it. Equal and opposite forces, same name, same, that's a complete free body diagram. Now think about this. If I knew the value of F, now I've only got 1, 2, a grand total of 3 unknowns. I need 3 equations to completely know this thing versus 6 the previous way around. That right there is why recognizing 2 force members in free body diagrams is hugely valuable to us folks. Sometimes you've got to see it in order to be able to solve the problem, otherwise you'll never have enough equations to solve it. So that would be good. That's also fine over there. Either one of those perfectly fine. Questions on that one, anybody? Okay, good. Let's be done. Let's get our eval out of the way then, folks. I'm gonna pass around a blank piece of paper just like we did the last time. Remember, this is the last of these. We won't be doing any more of these.